So, today we'll discuss resting membrane potential. What is resting membrane potential? It is the difference of potential between the outside and inside of the cell. In a neuron, this is about minus 70 millivolt, whereas in a skeletal muscle it is minus 90 millivolt. Now let us show the difference in concentration of different ions between the extracellular fluid and intercellular fluid. You can see in the intercellular fluid, the potassium concentration is 155, all concentrations in millimole per liter. So potassium concentration in the intercellular fluid is 155 millimole per liter. In sodium it is 15 millimole per liter. If you compare, potassium concentration in the intercellular fluid is 155 millimole per liter, whereas outside the cell, potassium concentration is 4 millimole per liter. In case of sodium, outside the cell, the concentration is 150 millimole per liter, but inside the cell it is 15 millimole per liter. Whereas in case of chloride, outside is 110 millimole per liter, and inside is 10 millimole per liter. Chloride concentration inside the cell is 10 millimole per liter. Now, what happens normally? We can see that because the potassium concentration is very high inside the cell, it will tend to go out of the cell, and as it is a cation, with the exit of potassium, the inside of the cell becomes electrically negative. But once this intercellular fluid, intercellular compartment becomes negative, it will attract the outgoing potassium ions towards inside the cell. So the electrical gradient will be directed inward, and electrical forces, gradient of electrical forces will go inward, whereas the concentration gradient of potassium will go outward. So at a certain electrical potential, this electrical gradient and concentration gradient are equal, and that is the actual resting membrane potential. That is called the equilibrium potential of potassium. In case of potassium, it is this equilibrium potential, and equilibrium of potential, this comes to about minus 90 millivolts. That is, equilibrium potential of potassium is minus 90 millivolts. So here it is shown that cell interior remains electrically negative due to potassium exit. Cell interior becomes electrically negative due to potassium exit, but then the two forces act. Here is Cg means concentration gradient, so here it is shown more clearly. Because due to concentration gradient, potassium is going outside of the cell, and due to electrical gradient, potassium ion is drawn towards the interior of the cell. Because the cell interior is now negative, and it attracts the positive cations inside the cell. So at a certain potential, which is the equilibrium potential, these two forces are equal, that is concentration gradient is equal to electrical gradient. Now, Nernst equation, we can calculate that by mathematically, and that is the Nernst equation. It is given by the Nernst equation, which is Ek is equal to RT by Fz into Ln, that is natural log, into potassium concentration outside, K plus O by K plus I. Now, if we put the actual values here, it comes to 61.5 log to the base 10 of 4 by 155. It can be calculated, and it comes to minus 90 millivolt. So we find that Ek, that is equilibrium potential of potassium, is minus 90 millivolt, and in the same way we can calculate the equilibrium potential of sodium and equilibrium potential of chloride. and ENA or equilibrium potential of sodium is plus 65 millivolt and equilibrium potential of chloride is minus 70 millivolt. Thus, we can calculate the equilibrium potentials of the different ions. Now what happens, potassium will try to maintain resting potential at its own equilibrium potential, which is minus 90 millivolt, whereas sodium will try to pull the RMP to its own own equilibrium potential, that is plus 65 millivolt. And chloride also try to maintain RMP, that is resting potential, minus 70 millivolt. But about chloride, it should be noted that chloride has no active pump, unlike sodium, potassium, ATPase, which is the pump forcing the movements of sodium and potassium. So chloride does not actively influence resting membrane potential. Now resting membrane potential depends on permeability. Now the permeability of potassium is much more. It is 10 to 25 times greater than sodium. So resting membrane potential is much closer to EK, that is potassium equilibrium potential, than to sodium electrical potential, just because permeability of potassium is much more. So actual value of RMP in neuron comes to about minus 70 millivolt. Equilibrium potential of potassium is minus 90 millivolt and equilibrium potential of sodium is plus 65 millivolt. But because permeability of potassium is much more than that of sodium, the resting membrane potential is much closer to EK and it is about minus 70 millivolt.